Problem number 5 describes a system of charges like this, a plus charge here, here, and here, and asks rather simply what is the potential energy of this system. The first thing to realize about this is where would the potential energy of this system come from, and you just have to imagine the assembly process that you would have to go through to get the 3 charges to exist like this. So say I covered these 2 here and 1 charge exists in space and I wanted to bring another one next to it. I'd be in a situation of having to take a positive charge from somewhere, say way down here, and start pushing it closer and closer and closer and closer and closer to this positive charge until I get to this spot, then nail it down somehow. But because these 2 charges are near each other, they contain potential energy between them, because if I release this charge again, it would zing off down that way. So I'd had to put energy into the system to assemble it, and that's the potential energy that now exists between these 2 charges. And the same thing would happen then if I had these 2 charges stuck here, and I wanted to bring the 3rd charge near them. I'd have to take this 3rd charge and bring it in, say, from way over here off screen, keep pushing it against the repulsive force of this charge and this charge to get it into this space. And when I let go, that energy that I used to push it in place now is existing in the system. So I'd like to know the potential energy between them. We have an equation that we sort of developed in class for the potential energy between 2 charges, and U is our symbol for potential energy. So it's going to be K times Q1 times Q2 over R. So it looks very much like Coulomb's law, but it's slightly different. There's the K, the 9 times 10 to the 9th. These are the 2 charges involved, and those are the separation between the 2 charges. So you have an energy equation. If you want to know the full potential energy of the system here, you'd have to add the potential energies that exist between all 3 of these charges here. So we can just start sort of forming an equation like that, if you will, here. So the total potential energy, I'll call it U total there, is going to be K times Q1 times Q2 over R. This is probably a good time to go ahead and number in the charges. So I'll call this charge 1, charge 2, and charge 3. You can fill in the values yourself. That looks like they're in the book here, that are in the problem. So these are the 2 charges here, the potential energy between charges 1 and 2. In other words, the potential energy that exists between these 2 charges. I'll continue to add in the potential energy that much also exists, say, between charges 2 and 3. So I can call that Q2, Q3 over R. There's the potential energy that exists between those charges right there, and we should probably be a little more careful about labeling the R's. This R here is the distance between charges 1 and 2. This R here is the distance between charges 2 and 3. And lastly, we'll have the potential energy across charges 1 and 3 like that. The distance will be found using the Pythagorean theorem of this sort of hypotenuse right here, but we'll call that R13. So we can start to find that distance as we'll need. So I'll go ahead and just add that in here as the last potential energy, plus K, Q1, Q3 over R13. So this would give the total potential energy of this 3-charge system right here. You could just fill in the numbers and do your calculation now. You could factor out a K and anything else that might be in common among all the terms there. And if I go ahead and do that and plug in and do the calculation and so on, I'll get that the total potential energy of these charges here, my U total, will come out to be about 2.82 times 10 to the minus 6 joules here. And that's what I get for this particular problem.